In this section, let us discuss about memory interfacing. Memory is the integral part of microcomputer. Whenever we write a program that is stored in memory, either it may be an instruction or it may be a data, everything is stored in memory. So processor is a separate IC and memory is a separate IC. Now this memory IC, it requires some signal requirements. Whenever we want to write something into the memory or whenever we want to read something from the memory, it expects some signals like read bar, write bar, chip select signal, etc. Similarly, if you look into the CPU, whenever the CPU wants to read something from the memory or whenever it wants to write something into the memory, it will initiate some signals. So in the case of interfacing, what we have to do is, we have to design a circuit such that the signals which are generated from the CPU whenever it wants to read a data or write a data into the memory should be mapped with the signal requirement of the memory. That is what we have to do in interfacing. Okay. So, if you take 8085 for example, we have already discussed that there are 16 address lines. So, using 16 address lines, we can have the maximum memory of 64K. That means the 64 kilobyte of memory can be directly interfaced with 8085 using 16 address lines. But generally, when you design a project using 8085 or microcontroller, it is not necessary that we have to make use of all the 64K. We may require 8K EEPROM and 8K RAM. Now here let us discuss how to design a circuit for interfacing 8K RAM first. Okay. Let us take, this is the problem, that is interfacing of 8K RAM with CPU. Okay. So while designing the interfacing circuit, you have to follow certain steps. Number one is, we should find out how many address lines are required. How many address lines are required to interface the memory with CPU. For example, if the question is draw the interfacing diagram for 8K RAM, then this is the formula you should find the number of address lines. 8K equal to 2 to the power of n, where n determines the number of address lines. So this is 8 into 1K, so I can say 2 to the power of 3 into 2 to the power of 10 equal to 2 to the power of n, so where n equal to 13. So we can understand that the number of address lines required to interface 8K memory is 13 address lines. Okay, this is step number 1. Then in step number 2, you should connect the data lines. The data lines of CPU should be connected with the data lines of memory. Data lines of CPU and memory should be connected. Number 3 is, we have to form a decoding logic. A proper decoding logic should be designed for address mapping. Okay, these are all the 3 steps. And one more thing is, the proper control signals should be connected between CPU and memory. These are all the 4 steps. Okay. Let us the diagram. Okay. So let us take the CPU where we want to interface on 8K memory. So here is the 8K RAM. 8K RAM. Now the first step is you have to identify the number of address lines for interfacing 8K RAM. As we have already discussed, 13 lines are required. So what you have to do is, here the address lines A0, A1 up to A12, it should be directly connected with A0 and A12 of 8K RAM. Actually in 8085 you will be having only 80 to 87. That should be latched. After the latch you will get A0 to A7. Then from A8 to A12 can be directly taken from CPU. If you look into the pin diagram of 8K RAM, there will be a provision to connect 13 address lines. So directly you can connect these address lines from A0 to A12. The idea is, by varying between these 13 zeros and 13 ones, you will get the 8K of different locations. 8K of different locations. Now the second one is, you should connect the data lines D0 to D7. That should be directly connected with the data lines of memory IC. Then there are three control signals. One is called IO bar, M bar, another one is read bar, another one is write bar. So you can connect these three into one decoder 74LS138. So that we will be getting 8 different combinations of these three input signals. So what we require is memory read bar. You get this combination of signal. You connect it with the read bar of memory IC. And another signal required is memory write bar. This is memory write bar. This should be connected with write bar of memory IC. Okay. Now this every memory IC will have one more signal called chip select signal. If you want to make use of this memory, whenever you want to read something into the memory, or whenever from the memory, or whenever you want to write something into the memory, first of all the chip select signal should go slow. The chip select signal CS bar should be low. So for this, now for designing this chip select signal, the extra address lanes can be used. Here you see you have A13, A14 and A15. So this is what they call it as a decoding logic. Just I can use one NAND gate, and this can be connected with this chip select signal. Now if you look into this A0 to A15, as far as this A13 and A14 and A15 are concerned, always it should be 1, then only the chip select signal should go slow. So you can vary the signals from A0 to A12. You can vary, that is, we can vary between 13 zeros to 13 ones to get 8K different locations. Whatever may be the combination between 13 zeros and 13 ones, these A13, A14 and A15 must be 1. Then only this will become 0. It will enable this chip select signal. So this is what, as far as the hardware is required to interface the memory IC with CPU. Now the next step is, you have to find the address space. Suppose the total number of the total memory locations available as far as 8085 is concerned, 64K. In the case of 8086, it is 1 MB, where there are 20 address lanes are there. Now you should go for another thing which is called address mapping, because within this 64K, this 8K RAM can be mapped anywhere. That is based on this decoding logic. Suppose if the decoding logic is like this, let us see what is the address map of this memory. So now, for finding the address map, right? Let us take this is A0, A1, A2, A3, A4, A5, A6, A7, A8, A9, 10, 11, 12, 13, 14 and 15. So So as far as A0 to A12 is concerned, on may be 0. Start from 0, 0, 0, 0. That is the minimum address. The maximum combination is it may be 1, 1, 1, 1, 1, 1, 1, 1. So irrespective of the any combinations between 13 zeros and 13 ones, this A13 and A14 and A15 must be 1, must be 1. Then only the chip select signal will be enabled. Now if you find the address, right, 1, 2, 3, 4, right, this is, you can say E, 1110 is E. So the address mapping is E0002 FF. If you subtract E000 from FFF, you will be getting 1FF. If you convert this 1FFF into a decimal number, you will be getting 8 into 1024 different locations. Now, whenever you do programming in lab, microprocessor kit, there are different companies like VI Microsystem is having, Frontline is having, and ALS. They are the popular kit manufacturers. You can see every kit have its own starting address. Somebody may have a starting address of 8,000, someone may have 4,000. That is because of these reasons. Suppose if the decoding logic is like this, your address space for this memory is E0002 1FF. That is our working space. Instead of this, suppose if I use one inverter here, I can use one inverter here. So in this case, A13, irrespective of the combinations between 13 zeros and 13 ones, A13 must be 0 and A14 and A15 must be 1, 1. Then only the chip select signals will be low. Now if you find the address, this 1100 is C. It is C0002. Then 1101 is D. DFFF. Suppose if the interfacing diagram is like this, if the kit manufacturer has the interfacing diagram of like this, then that kit starting address is C000. That is why you can see the different manufacturers, they might have mapped their memory according to their design, according to their interfacing design. Now here again, if you subtract C0000 from DFFF, you will be getting 1FF. So the total number of memory locations are same. But we can map the address, we can map this memory anywhere between 64K, anywhere between 00002 to FF. That is, depends upon this decoding logic. So interfacing a memory with this kind of decoding logic, they call it as full decoding system. The idea is, in the case of full decoding system, all the address lanes are to be used. Because for interfacing 8K memory, 13 address lanes are enough. But even though the extra address lanes are used for designing the chip select signal. But in the case, this is called full decoding logic. In the case of partial decoding logic, what you can do is, what is the required signals are from A0 to A12 that can be directly connected. Then here, instead of using this kind of decoding logic, just I can take A13 alone and I can connect with chip select signal. And I can leave that A14 and A15 as free. But anyhow, while specifying the address, now the condition is from A0 to A12, you can vary between 13 zeros and 13 ones. For enabling this IC, the chip select signal should be always low. So the condition is the A13 must be low. Always it must be low, irrespective of the any combinations between 13 zeros and 13 ones. But these two signals are kept open, A14 and A15. Here what will happen is, see, if you don't connect this A14 and A15, suppose if these values are 1, 1, 1, the address is C0002 DFFF. Now, because these two signals are not connected, suppose if these signals have the value of 1010, now the address pool is 80002 9FF. So these two, now here, if you specify the memory location 8000 or if you specify the memory location of C000, both will point the same memory location. Because these A15 and A14 are not at all connected with the decoding logic. It is kept open. So I can say that by using these two lines, we may get 4 different duplicating addresses. Every memory location will get 4 duplicating addresses. So if you interface using this kind of technique, they call this as partial decoding. If the system requirement is very minimum, you can go for partial decoding. We require only one EEPROM and one RAM. It is advisable to go for partial decoding. Otherwise, if the requirement of memory is more, it is advisable to go for a full decoding logic. Otherwise, you will get a lot of confusion. Every memory location will have a duplicating address. Whether you specify C000 or you specify A000 or you specify this 0000, both may be 0 also. So you can say one more duplicate address is 000. So every address will have 4 duplicating addresses. It will lead to a lot of confusion. Okay. Now in the case of full decoding system, if you take the previous case, right? Okay. This is what we have drawn, where A13, A14 and A15 should be 111. Okay. Now by using these 3 address types, these kind of 8 different chip select signals can be obtained, 2 to the power of 3. Because I can use one inverter here for one combination, for another combination I can use 2 inverters. So that time this must be 1, this must be 0, 0. So this kind of 8 different chip select signals can be obtained. So from this what you can understand is, these kind of 8 8K RAMs can be interfaced with this CPU. So 8 into 8K is total memory is 64K. Okay. So this is what this is how they design the interfacing logic between memory and CPU. The another important thing is, if you want to, instead of RAM, if you want to interface a ROM or EEPROM, erasable programmable read-only memory, what to do? Right? Supposing the question is, draw the interfacing diagram for interfacing on 8K EEPROM with 8085 or any CPU. In this case, what you have to do? See here what is required is the same thing. First of all, you have to find out how many address lines are required. Obviously, for 8K require 13 address lines. So 13 address lines we can connect from A0 to A12. The first step is over. Similarly, the data bus. You have to connect the data bus from this memory to CPU. Now, as far as EEPROM is concerned, it is read-only memory. So there is no write bar signal. There is no write bar signal in the. If you look into the pin diagram of a EEPROM IC, there is no pin called write bar. So you need not connect write bar signal. It is not possible to connect write bar signal. You can connect only memory read bar with the read bar. The another thing is, as far as this 8085 is concerned, once if you press the reset key, the program counter is cleared. So if the program counter clears means what? That always the execution starts from 0, 0, 0, 0. So if it is an EEPROM, the starting address must be 0, 0, 0. So in decoding logic, there is no other go. What you have to do, you can do like this: one inverter, another inverter, another inverter. Put a NAND gate and like this. You connect with chip select signal. Okay. Now, if you form a decoding address from this is A0, A1, A2, A3, A4, A5, 6, 7, 8, 9. Right, as far as A0 to A12 is concerned, all may be 0. And the maximum combination is all may be 1. But as far as this A13 and A14 and A15 are concerned, it must be 0. It must be 0. If it is 0, here you will get 0. Not only the chip select signal will be enabled. So what will happen? Now the address is, we will get the address of 0, 0, 0, 0 to 1 F, F, F. So this is your EEPROM address. This is your EEPROM address. If it is an EEPROM, this is an EEPROM address. Generally what they will do is, if the question is like this, draw the interfacing diagram for interfacing, one 8K EEPROM and one 8K RAM. So in this case, the same diagram can be used, and instead of these kind of decoding logic, you can use one decoder which is named as 74LS138. Right? In the case of 74LS138, for 3 input signals, a 3 to 8 decoder, it will generate 8 different output signals. If both are 0, 0, 0, you will get a low signal from O1 bar. So what you can do is, this can be connected with the chip select signal of EEPROM. Now, whenever the signal is 0, 0, 1, the another line, O2, otherwise you will take this is O0, this is O1 should be low. So this chip select signal can be connected with the chip select signal of 8K EEPROM, 8K RAM. So you can, but if you use one decoder of like this, these kind of 8K memories can be interfaced. If it is an EEPROM, you should see that the starting address is 0. If it is a RAM, you can map anywhere. Suppose if you do like this 0, 0, 1, 0, 0, 1, then 0, 0, 1, 0, 0, 1. Now the address you can see, this is 2, 2, 0, 0, 0, 2, 3FF. So this is the address of the RAM. This is the 0, 0, 2, 0, 0, 0, 0, 2, 1FFF is address of EEPROM. So you can interface the memories like this.